everybody. This is Divya Agarwal with my third lab on circuits in Physics 2 at Georgia Tech. Here's a brief overview of what we'll be going over in this lab. Here's an introduction. So the purpose of this lab was to predict the behavior of circuits containing resistors in series and parallel and use multimeters to measure the actual values of conventional current and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors. Here's a brief overview of our results. So you can see that theoretically the current in the first system was supposed to be 0.0204 amps, but actually it was 17.1 milliamps, 20.4 milliamps, and it was actually 17.1 milliamps. And then for the charge times on the lower resistance and high resistance capacitors, it was 12.7 seconds charge, 9.19 seconds discharge for the lower resistance, and a 58.8 second charge and a 49 second discharge for the high resistance bulb. So this makes sense because if it has a higher resistance, then it'll take longer for the current to get through, right? So fundamental principles. So we use the node rule, the loop rule, and Ohm's law in this lab. So the node rule basically states that current flowing into a node is equal to the current flowing out of it. The loop rule shows that the sum of all the electrical potential energy differences around a loop is zero. Not potential energy, sorry. Sum of all the electric potential differences around a loop is zero. And then the Ohm's law provides that current through a conductor between 2 points is directly proportional to the voltage across the points. So like each one of these deals with like one part of V is equal to IR, right? So the loop rule is the V, node rule is I, and then Ohm's law has the R. So here's the first part on the lab in series circuits. So here's a little bit about what our circuit actually looked like. So we had the battery, and then we had it hooked up to the ammeter, and then we had the resistors in series, and then we had it hooked up to the other ammeter, and then back to the battery for one of them. And then one of the other ones, we had the resistors hooked up in series, as you can see in the bottom right, in parallel. And then on the left, you see the capacitor, one of the capacitor circuits with the light bulb. So here's some of our data here. So we know that, as I mentioned before, the current in the first resistor through the first resistor was just the current through the first section was 17.1 milliamps. The current through the second section was 17.3 milliamps. So they are supposed to be the same, but some approximation error maybe or some calibration maybe would have fixed that. And we know that the brown resistor is 100 ohms and the gray resistor is 47. So we realized that after switching the ammeter to the voltmeter reads 0 because there's no potential difference across the wire, and that's what we were measuring across. And the ammeter reads slightly higher, 18 milliamps, because of the different setup of the circuit, possibly parallel versus series. And when we were measuring the voltages, we found that the battery was negative 2.6, and that's like one of my errors, I guess, because as long as the battery was negative and all the components were positive, or the battery is positive, all the components were negative, it would have all worked out to 0, but the sign is still technically wrong. And yeah, you can see the voltage values. So there's 1.7 volts difference through the brown resistor, 0.7 through the gray resistor, and theoretically there's supposed to be no difference in the ammeter because it has no resistance, theoretically, but obviously in real life there will be. So the sum ends up being negative 0.12, but it should be 0 because of the loop rule. The voltmeter has infinite resistance, theoretically, so it doesn't draw any current.